Morning. So I'm happy to present the work of my student. It was a paper of my student, but as they didn't come, so then I will present their work. So this work based on using radio frequency platform for detection of CO2, but with different functionalization. And it was with collaboration with many institutes and university in France. So let's speak about the motivation. So our motivation here is the detection of carbon dioxide gas sensing. As you know, we need to detect this gas for atmospheric science, industry, and health application. When we want to detect some gas molecules, so we need a chemical sensor. And for that, we need to functionalize the transducer. Here you have also an overview of the existing markets on sensing, so which published by ISORG in 2020. We can see that 100% of existing gas sensors are electrochemical, 12% DIR, and 9% are based on semiconductors, so MOX sensors. So all of them, for example, the electrochemical is low cost and we have low also energy consumption. However, has a short lifespan. And for example, MOX, so we know that we should use a high temperature to make a height on the resistance in order to dissolve and adsorb materials. So then we try to find the compromise between all of this, because we are looking for the low cost from the point of view of markets, and also how we make functionalization easy. In this case, we use it, so we propose a solution of using microwave sensor. Let's present the principle working of this kind of platform. So a microwave sensor is based on topology of filter. So it's like a radio frequency filter. So we can design different geometry. We can make a filter, passband filter, rejector. It depends on what we want to do. So for this application, we developed the geometry based on a filter passband and working around 3 gigahertz. And also this platform is based on a flexible substrate, which is capped on here. And on the top, we print our electrode. As you can see here, finally, we make a resonator that you can see here. So we have the gain of this structure and its phase here. So for the detection after, we will try to measure the shift on frequency or the attenuation in decibel. And also in this kind of geometry, usually you are using the same two topologies. So the first will serve for detection because both of them will detect also physical surrounding parameters like temperature and the light pressure. But when we add a sensitive layer, and then will be more specific to the target gases. So here we are showing the fabrication of this sensor. As you can see, we developed it with our partner, chemist partner, two kinds of materials, sensitive material. So here you can see the two materials, coated materials. So the one is the commercial HBPI, and the second is the HBPI functionalized with SILA, with the chemist. And you can see also that the thickness of these two sensors and the two fabricated resonator give us this response which is close to the simulation, what we were expected, just with more loss, which is normal. When we fabricate and simulate, there is losses that we cannot integrate. So here there is an FEM imaging. So you can see that here it's the image of the commercial HBPI, and here is the HBPI sealant. You can see that the rugosity of HBPA sealant is 10 times higher than the commercial one. And this maybe after will help us to interact more with the targeted vehicles. So from the fabrication, then we developed two test bench for this measurement. So we did experiment for CO2 detection for the generation of the dioxide carbon gas. And also we developed another test bench in order to introduce to see the behavior of the sensor under humidity and temperature. So then we can have idea about the interference. And all of that in point of view of electrical. So we add vector network analyzer with the 4 ports in order to characterize different two kinds of sensor here. And also we add the commercial sensors in order to follow the atmospheric surrounding. And we use a Raspberry Pi in order to convert all this signal and to make the data processing. So here you have the results of the first measurement of humidity. So we started with the humidity, then temperature, and then CO2. So for humidity, we can see that the resonator based in HBPA, so give a sensitivity of I think 35 kilohertz at 1% RH and 1.09 megahertz for humidity, relative humidity at 60%. So also the recovery time was estimated around 20 and 44 seconds on the other for the other one. And for the second HBPI sealant, you can see that the sensitivity was estimated to be around here 0.15 megahertz at 1% RH and 0.34 megahertz around 60%. So we can see that HBPI sealant is less sensitive to RH compared to commercial. So this sealant brings hydrophobia of this active layer, which we want for the real life detection. So then we did the same experiment, but for the detection of temperature. So here you can see that the commercial HPP gives a sensitivity of 1.55 megahertz, and the HPP sealant also show that is less sensitive to temperature, which is good news for us. And then from that, we move for the measurement of CO2. So as you can see here in gray color is all our generated concentration, and on the red and some green dots is our measurements. So here we are showing directly the differential answer. It means that we take into account all the influence of the other part. So and the CO2 was between 0 and 10,000 ppm. So you can see that the response very inversely with CO2. It means that when we increase our CO2, that our frequency decrease. And but the good news, we did this 5 times, and we find some response, as you can see on this point, because we put all signals that will make us happy to see the repeatability of this platform. So here you have comparison of the two materials, so HBPI sealant and commercial HBPI, and you have the sensitivity here. So we find that HBPI finally sealant is more sensitive than the second polymer also. So here you have comparison of specificity to CO2 and RH, and we can see here that HBPA sealant is more specific to CO2 compared to RH, and we see that the commercial is more specific to humidity, relative humidity, comparing to the CO2 gas. So we made a hypothesis that from the chemists that the tertiary amine function that we add, it means the sealant, the functionalization of this material is more reactive towards CO2, and also, as you remember, the film's morphology provide a greater surface area, as we saw for the other material. From that, we can conclude that commercially available HBPA was functionalized to obtain a hydrophobic material, which is HBPA sealant. And also this functionalized enabled to reduce RH to be hydrophobic and also temperature influence and increase sensitivity to CO2. However, at 0% relative humidity we are speaking, because this detection of CO2 was around 0%, so in nitrogen. However, I don't know if I didn't speak about that. You can see that when the sensor is under humidity at 60%, we cannot detect CO2. So this is something that we should handle for the next experiment. And our perspective are to explore various functionalization techniques in order to address the influence of RH on CO2. And also, it's to use also machine learning prediction algorithms, so to go for detection on the realistic world. What is the next for us? So thank you so much for your attention.